Okay, let's get started. So this is the illustration, or if you prefer, simulation for what we did last time. So this is just the beginning, so we need to do some more work here. So this is just a function 1 the reciprocal, and we just want to learn how to use sequences in order to study the behavior of the function that is either around the point of x, okay, a particular choice of a value of x. So this one, even though it looks like a sequence, it's just ignore that. The point is that this is just a graph. Okay, so that's the very first thing we worry about is the graph. So I could even, to make that point, I could do it this way. I just don't want to. Here's this one. Okay. So as you can see, it could be turned into the graph. So this is where everything is happening. Imagine this is the graph of the whole thing, and we're gonna see what's happening to this function around 0. So x equals 0 is here, and we want to see what's happening, what function does to these x's. So as we're approaching from right to left, 0, then it already suggests what's happening to y's, but I want to be more specific so that we could not just refer to the picture, but also I can later do it in a more consistent way and really rely on the definition of the limit of sequences. So this is what I'm going to do. I'm going to create first the sequence of x's as we did last time. So this is the outline. This is the outline. This was going to happen. This little picture over here. So once again, sequences of x's first on the x-axis. The choice already has been made at 1 n. Okay, so let me do that. Okay, so I'm going to put in here. And so starting with 1, this one equal 1 plus 1, and so on. Okay, in the meantime, these will be x's. Okay, so there will be x is xn. Okay, so this is xn. Okay, or an. This is our sequence of x's. Okay, so it will be simply the reciprocal, right? We are applying the same formula. So it is equal to 1 over this thing. Okay, as you can see, it continues on. Okay, so let's do that. So I don't need a lot of points, but just what is it doing? Okay. So it recomputes all these points, and now what I want to do is to take these. This is my sequence. The second column. Well, this thing is not working. This column is in fact x's, and I want to put them on the x-axis. So it just is the very first step. Okay. So what I do is I pick. So I add, select data. Okay. So I add. So this is axis, or xn if you prefer. Okay. So x values will be these. Okay. X values are these, and y's should be zeros. I think this should work. Well, maybe not. Now let's just put 0 there. Let's see. Okay, where is it? Okay. No. I can see only 1 point for some reason. So these are the points. Okay, it doesn't quite understand. Let me do it this way. Let me put a 0 here. So these are x x's, let me put a 0 here. So these are x's, and they correspond to y's. Okay, so that's what I'm plotting. I'm plotting x's and y's, but initially on the x-axis. Okay, so once again, this is one point, but there is a bunch of them. So let me once again select data, xn, and xn had been chosen y's. I'm choosing y's. These are the y's. Okay, that should work. Okay, you see them? Unfortunately, they gray in color for some reason. So let's change the color. Okay, you need. Damn it. Where is it? Everything is just moved around. I just don't recognize anything. So anyway, so the green dots are on the x-axis. This is sequence of 1 over n, as I explained here. Okay, so 1 over n, we are making specific this idea of x approaches. This sentence is x approaches 0. Okay, what does it mean? It means that we pick a sequence of x's that is the limit of which is 0. Okay, so sequence 1 over n is on the x-axis. Okay, so now what we do is, now let's find the corresponding values. Let's get first the points on the graph. Okay, so these points will have we have counterparts on the graph. So I'm adding more data. So we select more data. Okay, so I'm adding. So let's say graph. Okay, so x values are the same. Hold on a second, I got ahead of myself. We need to compute y's first. So this will be yn. And there, how we just compute them as reciprocal. So it's equal to 1 divided by the value of x. Okay, and we spread it down. That's not right. What the hell happened? Okay, I'm referring to the wrong one. Okay. Hold on a second. Yeah. Oh, yeah. No, that's right. That's right. So it just looks surprising, but actually these are x's, these are y's, and let's show that they do belong to the graph. Okay. So I'm selecting more data, and I'm adding data which is on the graph. X's are these. Okay. And y's are those. Okay. Okay. See them? So each point xn on the x-axis, which happens to be unfortunately gray, is now corresponds to those yellow dots on the graph. Okay, so indeed we're staying within the graph. For the complete picture, what we need here is now yn. Okay, so that is uncomplicated. I just because we already have y's. To have the counterpart on the y-axis, we just have to make x equal to 0. Okay, so we're adding one more, and that will be yn. Values of x, as I said, is 0, so these are the ones, and values of y's are these. Okay, all right. Okay, so this is, let me make it slightly larger so I hope you can see what's going on. So first of all, starting with the orange, that is the graph itself. Okay, so it's kind of incomplete, the orange. In fact, maybe I'll make it thinner so it wouldn't be as, well, I wish I could just, the orange one, this one, fill. Okay. Why is it all looks different? It all looks different. Nope. It just picks one point. Okay, so the orange one is the graph of the function itself, so we just know where stuff is going on. Then we have gray points on the x-axis. These are xn1. That's reciprocal. This is the column. Then using the graph, remember how we compute values of functions. When x is given, we find the counterpart going vertically, right, like this. From this, if this is x, then this is a point on the graph that we're going to use. And then what we do once we found that point, we're going horizontally, so that's the answer. Okay, so we do it to every single point that in our sequence, which you can see how it accumulates towards 0. Okay, and when we found the counterparts on the y-axis, and then this is these points, the blue ones, are supposed to tell us what's going on with the function. Everything. Unfortunately, what is missing here? Okay, let me change something. Let me add arrows. Let me add arrows because those blue points, they are not going down; they're going up. Okay. So as the gray points go right left, the orange points going kind of diagonally up, and the blue points going up. So it is actually probably makes sense to have arrows. Okay, that's not it. Let me try to remember where that thing is. No. Okay, let me change the chart type to these. Where are the arrows? Where is all this stuff? Design and format. That's exactly what I don't need. Not design, not format. Layout. Okay, do you see the word layout anywhere? This is...
There might be arrows on format.
What?
Format. There might be arrows over towards the left. I don't know if you can put those on the graph. Over there where it says...
No, that's no, I'm afraid that's not it. So let me try again. Format, okay. Axes, it's all here somewhere, but it's format that data series, primary axis, secondary axis. That's not it. Okay, so that's not helping really. Okay, so let's just think in terms of dots. So the challenge is here is just to see the direction at which the points progress. So certainly at the bottom on the x-axis, I think it is clear that the accumulation is from right to left. So the sequence 1 is going from right to left. In the meantime, the find that we find of y, it seems that everything is, you might think it's going down. It's not going down, it's going up. Okay, so these points are going up. Okay, so that is the dynamics that the function produces. So let me write that out over here. So 1 going towards 0, that is my, say, xn. Okay, and then I take my function, which is this one. So yn is equal to 1 over 1 which is n, and it goes to infinity as n goes to infinity. Okay, so in other words, the function creates a new sequence from the old. And xn is the original sequence as a tool to study what's going around 0, and then the function produced a new sequence. Okay, so the sequence that is produced is really simple. It's n, it goes to infinity, and that is explains in a numerical fashion what has happening to the function itself as x approaches 0. So once again, we read this x approaches 0. Okay, and we read this as y approaches infinity. Okay, so that is the behavior of the function that we have discovered. Certainly it is visible on the graph to begin with, but it's what? If I turn turn off the sound too. Machine. Okay, so the graph of itself, which is still made of orange, the orange graph that we started with, is visible, but the numerically we see that the conclusion that y goes to infinity is right here. Look at it. So as you can see, start 1, 2, 3, 4, and then 17, and you realize that if I continue with these points, they will go to infinity. Okay, so so that's one thing that we discover. One case of what could happen at a point of a function we have discovered. There are other behaviors that are possible. So let's take another one. And the one that we did last time started with last time is simply what is it? Sine x. Okay. So so this was 1 over x, and now we're doing sine x. So my function here will be sine x. But otherwise, the behavior will be the same. Okay, so sine x. Okay, so that is, we entered here sine of this value. Okay. Okay, so I didn't put it very close. Okay, let's try again. Okay, so we'll get just a few. Okay. Okay. So that's my sine, which just happens to be kind of a small, but because it's stretched, but well, that's okay. So this is the orange is the graph of my function. It's sine. It actually passes through the origin, so we could probably add more values here with no danger. We're not gonna end up at infinity. So I could add some more like this. Well, it's actually going fairly slowly towards. Okay, so let's see. Okay, so that's the graph of sine. It will, once we resize, it will look like sine. So that's the graph of sine, and the graph of the sequence xn is still this. So we're still approaching from right to left towards 0. And now I just need to change the function over here. So this is still once again sine. Okay, sine. Okay, and. Okay, all right. So once again, the orange one is the graph of our function. Okay, the gray is 1 over n. Okay, we are approaching approaching 0 along the x-axis initially. Then the second step, you have to look at it as in 3 stages, 4 stages in fact. Graph first, the orange one. Second stage, we add xn to this picture. The xn, the sequence 1 over n, and the x-axis. The third stage is finding the point on the graph of our function. Those are the yellow ones, okay? And then from the yellow ones, we find the blue points on the y-axis, okay? So from this picture, what's the conclusion? Let me start over here. So we're talking about, so this was f of x is equal to 1 over x originally. Now we have f of x equal to sine x. Okay, so we went xn, it was still 1 over n, goes to 0. Y over n is sine 1 over n, which cannot be simplified. And so this is the question, what if you see from the graph here, so what's happening to y? It's also approaching 0, okay? So the behavior is kind of similar, actually very similar to the behavior of xn. Okay, so that's the conclusion that we make from this picture, that this also goes to 0, which happens to be also to the value of the function at 0. So x approaching 0, and y also approaches 0, which happens to be the value of the function. Okay, so what does it indicate to us is that there is no gap in the graph of the function, which we certainly can see from the orange line. Okay, So these are the two cases. There are other cases of what can happen to functions. So this is the good outcome. So this is the so sine x. This is 1 over x, which is, as you can see, the behavior is bad, good, bad. There is a, not only, this is really bad because the gap is not just not just a gap, the gap is infinite, right? The gap we are jumping from, we are ending up at infinity, okay? So, all right, so now, well, let's do one more example. The function is, okay, the function is sine 1 over x, okay? Sine, that's what's going to be, 1 divided by x. So it's kind of a combination of the last two. So one is well behaved, the other badly behaved, but actually you can see what's happening. So once again, the rest is the same, but the function is different. Okay, so instead of sine, we have 1 divided by this thing. Okay, and well, I just hope it's not going to break down. Okay. So ignore the blue stuff. That's what we just have to take care of. Take care of. The orange one is the bits and pieces of the graph of my function. Okay, so we will talk about that later. But the function oscillates so quickly that, as you can see, the gaps between points become so large that it's literally the curve does not look like a curve anymore. So it starts well, right? It looks like a curve, but then it starts to oscillate, and the Excel just has too few points in order to have any very meaningful looking curve. So let me explain that. So 1, 2, and 3. So 3 is f of x is equal to sine 1 over x, and in fact, let me. This will be the same, but you can guess the nature of the behavior. 1 over 1 over n, okay, which is simply sine n. Do you remember what the limit is? Sine n goes to infinity. So let me just plot these graphs here. Sine n goes to infinity. What's the limit? Does not exist. Right. Does not exist because sine oscillates. That's what we've learned about sequences, and now that knowledge we're trying to apply to functions. So sine 1 over n function, this is what the graph looks like. You can guess from this conclusion, you can guess what it looks like, also from the picture. So by hand, I can actually make a better picture than Excel. This is how the graph behaves of this function, sine 1 over x. Okay, so it as x approaches 0, you see what's happening to y. It oscillates, and not only it oscillates faster and faster. Okay, so that's what Excel produces for us here. As you can see, those orange dots are the dots of sampled curve. The curve I just drew, if you sample it, you end up with something that does not look like a curve at all. So it starts with okay, and then everything just falls apart. So let's confirm once again the investigation that we did. Do the same investigation here to confirm the limits. We already know the limit doesn't exist, so let's confirm that. 1 divided by. Okay. Okay, so as you can see, the I'm sorry, yellow. The orange ones is the curve. The yellow points are the points on the graph. Okay, so xn. Don't forget that gray sequence on the x-axis. Okay, so that's the where everything starts. There are or yellow points. That is the sequence on the graph, and then the values of y are the blue ones. So there aren't enough points, I'm afraid, in order to draw conclusions about the divergence. So let's do a little bit more. It appears that we just don't have enough data. So it does seem, it does look like kind of random. If you look at the blue points, they are kind of random, spread out, but it's really not. I think we can do better than that in order to illustrate what's happening better. So I'm gonna just add more data here. Okay, so these are the y's. Come on, grab it. Let's try again. Okay, so it's I'm just providing more data. Okay, you see the blue dots now? These are the y's, and this is supposed to be a sequence. It is, no matter in what order you follow those blue dots, you can tell that there is no pattern appearing. There is no one accumulation. It does appear that there is more density at the top and at the bottom, but really, if I could make more and more points, what's going to happen if I make more and more points? What?
More towards the middle.
Okay, if I make more and more points, what the picture of the blue dots will look like?
Just look like a solid line.
It will be a solid line. So let's confirm that. A solid line, indeed. So let me do that. So just want to have more data here. Stop it. More data. Scroll. Okay, here it is. It is indeed a totally solid line. So that's a sequence. You won't think of a sequence that they can fill an interval. And it not only does that, it does that in a kind of a uniform way by running back and forth in a seemingly random way, and that's how there are no dots spots left. So okay, that's the typical behavior that you might encounter. This is the third case. Okay, so the limit doesn't exist, even though it does not go to infinity. It's still bounded, but it goes to infinity, and the result is a very nasty run around oscillating sequence that fills the segment. So you can also think of examples. Imagine the same when you could fill a square. A sequence that, if you keep repeating it, will fill a square in a similar manner. You can probably imagine that. So that, a lot of behavior will be kind of unexpected, in the sense that you don't expect a curve to look like this. Okay, but when you have this kind of divergence, it actually does happen. All kinds of unexpected, unnatural behaviors. So once again, curves that look at it. In fact, the accumulation you can see in my picture over here. So if you see on the left, the swings of the line become so close to each other that they virtually they become invisibly indistinguishable, and so it becomes already like a rectangle. So if I just keep going with the orange here, this is what it's going to look like this. You can't tell the difference. And at first there's at least some gap, but if your line has any width, it will be just a rectangle, all orange. Okay, so that's what can happen to functions. So once again, two bad behaviors. So this is bad. This is certainly also bad. There is one good. This one is good. So as you can see, not only the limit exists, it's actually equal to the value that we care about, and we have to keep them apart. So That's, remember we talked about that, the continuity versus discontinuity and what kind of catastrophic consequences it might lead to if we don't. So okay, so let me then go straight to the definition. From this example, the definition of the limit of a function becomes fairly clear. So given a function y equal f of x, defined on an interval, say, on an interval that contains x equals a, okay, some value, except possibly x equal a. Okay, so what I'm saying here is the function is defined on an interval with possibly one point missing. So this is an interval. Let me make it clear that the interval should be open. An open interval. Remember, open intervals, it means that the endpoints are not included. But this is an open, it defined at every single point of the interval with the exception, possible exception of a. So say a plus 1, a minus 1, a plus 1. We are not assuming that the function is defined at that point. We already had 2 examples out of 3 where the function was undefined at that point. So if you take function 1 of x, naturally you cannot plug in x equals 0, but it doesn't necessarily mean that things are bad there. It could still be okay, as we see shortly. So that's why the setup is like this. So we do not assume that the function is defined there, and then we proceed to defining the limit. So then what we limit, well, let's say the limit of f y equal f of x as x approaches a is a number L that satisfies. So once again, look at the picture. This picture. Okay, so we have, well, probably this is not a good. This is a good picture, right? So we are describing a positive outcome. The second example, sin x, when, as you can see, the behavior of x produces the behavior of y, which is convergent. Okay, so x converges, y converges too. So that's what we want. That's a good thing. And then if it's not satisfied, then it's a bad thing. So the limit, it satisfies for any sequence xn convergent to a. Okay, remember this is 1 over n. We have f of xn converges to L. Okay, so very, very short, nice definition. The behavior of any sequence on the x-axis, as long as it converges to A, produces a sequence of y's, this is yn, that also converges to a number, L. Okay, that is the limit. Sometimes there is no doubt of as to what the answer should be, how to compute it. And the example of 1 over n was especially simple when you know that there is no L, no matter what sequence you pick. If f of x is equal to 1 over x and x is equal to a, then naturally yn is equal to 1 over xn. So now imagine that xn goes to 0, and what I was saying is a is equal to 0. Okay, so as an example, so f of x is 1 over x, y nth is equal to 1 over x nth. Okay, and then we know that xn is supposed to converge to 0. Then what do you say about yn? If the denominator of a fraction
does not exist.
yeah, or you say it goes to infinity. Either way it diverges. diverges, and that in that case we say that there is no limit. Okay, so in this diverges, the sequence diverges, so no limit of f at that point. By the way, you can see how what kind of problem we're tackling is that every point can be, it has to be addressed in this manner. So we picked one for 1OX, we picked the point where something is happening, something bad is happening, but really any point can be picked. So if I say I pick this point over here on the graph, and actually the function is well behaved there. Every point other than 0, everything is fine. Even though it swings up and down, it doesn't matter. And only at 0 something bad is to be expected. So notation, L is equal to limit f of x goes to a. Okay, so the definition expressed in terms of two convergent sequences. Start with a convergent sequence, xn. The function produces a new sequence, yn, which is also convergent. Okay, if that's the case, then we are okay. Okay, I want to emphasize that in contrast to the examples, we have to deal with any sequence. So we have considered in the examples one particular sequence, right? So 1ON, but the outcome should be the same. You probably, with this one, you can predict that it doesn't matter which sequence I pick, 1ON squared, or whatever I can pick. I could go also to the left. I could go with the negative numbers in the same manner. The outcome will be the same. You can probably predict that from the picture. And we will have to demonstrate that this is indeed the case. But for the time being, this is just what we've got. If there is one sequence for which the behavior falls down, there is no limit of yn, then there is no limit. Okay, so in fact, let me demonstrate that this is why this word is so important. Is this? So if I take my sequence of once again f of x is equal to, so that's another example, f of x is equal to sine 1OX. Okay, so at a equals 0 again, so let's review what we already did. Xn is equal to 1ON. Okay, yn is equal to f of 1ON, which is so sine 1 over 1ON, which is equal to sine n, and this one diverges. Okay, so that already conclude, so there is no limit by definition. Okay, but I want to demonstrate that it's not necessarily the case. It's not necessarily the case of such a bad behavior. So this is the bad behavior I'm referring to. It diverges, but we could pick xn such that yn of xn converges. Okay, so if you look at the graph again, let me plot the graph again. Can you think of a sequence of x, or rather points? Let's think in terms of the points on the graph. Can you see a sequence of points on the graph that is well behaved? And well behaved, I mean this is the picture. This is the picture. This is a well behaved graph. But if you forget about the orange part, just look at the yellow points. Yellow points, you can tell apart orange and yellow right here. Is it bright enough? Yeah. So can you think of a sequence of can we put yellow points on my graph over here, or any other color, so that it doesn't look as nasty as this sequence, as this sequence. So that's a nasty sequence, right? So, but can we be selective in choosing points so that the behavior is okay?
On the tops and bottoms.
Either tops or bottoms, that's right. So this is, let me pick those points. Let me take black. Okay. These are okay. Look at them. They behave just fine. It is a very convergent sequence. Yn, in fact, is equal to 0. Okay, so there is no trouble whatsoever. So that we could choose well-behaved points on our graph. Just to make it specific, let's choose xn. Xn such that f of xn, which is sine 1 of xn, is equal to 1. Okay, I want to have them to be on the same level. So let's solve it. Remember trigonometry? When is sine equal to 1? What angle, the sine of which is 1? What's the angle?
That one, 90 degrees.
Right. 90 degrees, so we're not using, so radians, please.
Pi over 2.
Pi over 2. Okay, pi over 2, so there we go. So this is the answer. It will be 2 over pi. I'm sorry, hold on, I'm getting ahead of myself. That's only 1 point. Pi over 2 plus, it revisits 1 every, what's the here? 2 pi, that's right. 2 pi n. So for each n, you'll get a new point. Okay, so that's exactly the sign is oscillate between -1 and 1. When you make a 2 pi turn, you will have 1 again, and then 2 pi, 1 again, and so on. So that's for every 2 pi n, you will have sine equal to 1, and indeed then we have a sequence. Xn is equal to 1 over pi over 2 plus 2 pi n. So it actually does converge to 0. You see that this converges to 0, right? Right, so because you have n in the denominator, so this is a sequence converging to 0, and it is f of xn is indeed equal to 1, so it's a well-behaved sequence. Doesn't matter, it does not, so doesn't matter. So just an example to illustrate the point, but this remains a problem. There's still no convergence, even though you can pick and choose and make it look good, but it doesn't matter. If one choice is bad, the whole thing falls apart pretty much. Well, there is one more example. Let me modify this example slightly. What if I have my function x sine 1 over x? Looks nasty. I made it even nastier than the last one. So sine 1 over x still oscillates as x approaches 0. In the meantime, but what's the role of x here? X approaches 0. So we multiply our oscillations by x, which approaches 0. So what does the graph look like? Well, x becomes the swing, right? X is swing, so sine 1 over x oscillates between -1 and 1. If you multiply by x, x becomes the swing. It will oscillate between -x and x. But x is going to 0, so what's happening to oscillations?
They're getting shorter.
Yeah, they get shorter and shorter, so this is what it's going to look like. So it oscillates faster and faster and faster, but those oscillations become smaller and smaller, and the conclusion is this one is well behaved, even though observe that this is undefined at x equals 0, yet the limit of f of x is actually equal to 0 as x approaches 0. Okay, so it does look very, very poorly behaved, but it does have a limit. Okay, so we'll continue this tomorrow. Okay, I have assigned the homework already.